All right, thank you. Wow, good morning again, Timisoara. How nice it is to be here. I'm super excited about being part of this conference, as I've been following the people from tim.js for quite a while now, and we've been in contact so much over like the past few years. So I'm really happy to be here and to be part of like the first edition. As mentioned, my name is Alex. People from Romania might instantly figure out by my thick accent that I'm coming from Cluj. You can find me on Twitter at Alex Moldovan. And very important, there's a link here, bit.ly/revo.js-alex. If you follow that link, you will have instant access to the slides if you want to follow along the slides. There are a bunch of links, usually in the bottom part, that you can also access afterwards and read at your own pace. I work at a company called Teleport HQ. I think the video is stuck here. Well, anyway, we do kind of like all sorts of crazy experiments with wireframe detection and code generation. If you're interested in that part, this is not the topic for today, so I'd love to talk with you about it, but maybe we can talk during the break. And as mentioned, I want to give a huge shout out to my local community from Cluj, JS Heroes. I know a bunch of you were at JS Heroes in the last years. I hope to see as many as possible of you there. Next year is going to be on the 23rd and 24th of April, so grab your tickets, come find me afterwards. I have discount links for communities, and yeah, I would love to see you there. And I have stickers, by the way. You know, I'm a huge sticker fan, so fortunately you can't see, but I just have to show you. My laptop is full of stickers, so if you didn't believe me, okay, now you believe me. Okay, so we're going to talk about performance today. And when I talk about performance, I like to set the stage with somehow how I feel like two kind of like truths about performance. Or two things that I like to share as ideas just to take away. So first of all, performance is something that performance problems will happen. So whatever we do, we will build sites that perform badly. And this is just like a truth that we just need to accept. On the upside, what I think a lot of people fail to realize is that we shouldn't be afraid of getting our hands dirty. Performance is not something that should be tackled by seniors, consultants, experts, professionals, whatever you call them. It's something that can be tackled by developers in the day-by-day activity. And one of the reasons why I talk about performance is to inspire teams, individuals, companies in general to bring these small tweaks, these small ideas that can improve performance in your day-by-day activity, right? So that you're not putting all the performance effort in the performance sprint or the performance iteration after the release when you realize that it's already too late. You actually bring it all at every step of the development process. And today particularly we're going to discuss about a specific branch of performance which is called rendering performance. What happens after the page is loaded, so we're not going to talk about prioritizing resources, about bundle sizes, about stuff like that. We're going to talk about how the app feels or how the website feels after we loaded everything and the user starts interacting. What happens when you focus on inputs, what happens when you hover over something, animations and stuff like that. So rendering performance is basically what happens when a change from JavaScript or CSS triggers a change on the screen, right? A new frame being rendered. And this rendering pipeline is composed out of a couple of steps. It starts from JavaScript because most of your changes will happen in JavaScript. Event handlers, asynchronous actions, data coming back from some endpoint. It usually starts there. It can, of course, start from CSS, but most of the times JavaScript is the main trigger of a DOM change, right? You can imagine that at this point, an element was added to the DOM or was removed or some change happened. The next step is the styling phase. In this phase, based on specificity, all the elements in the DOM get their computed styles. Next one is layout. When you start, the browser starts from the top left corner and starts arranging the elements based on positioning, displays, margins, the grid system, everything like the box model, everything that decides the position of an element relative to others or absolute or whatever the rules are. After you have the layout, after you have like the skeleton of the DOM, you have the paint operation. Now the browser can decide, okay, for each individual pixel, which color do I assign? Is it the border color? Is it the background color? Is it the shadow? Is it opacity? So basically it's deciding for each pixel which color to apply. And finally, the last step is the composite step. Because browsers are not, like the DOM is not necessarily rendered on a single sheet, if you want. It actually can be layered based on things like z-index, based on certain elements being promoted to their own layer. And keep that in mind because it will be important later. The idea is that you end up with a couple of layers of elements. And in the final step, the browser needs to decide, okay, which element is on top? Is it this model window or is it the background screen? Now, all these actions happen in sequence. Every action requires the result of the previous step to be able to work. Because of that, we need to make sure that this runs fast, because otherwise, because keep in mind, the browser, the UI thread of the browser is the UI thread, right? It's not the UI threads, so we will have a single threaded environment that pretty much has to run this rendering pipeline for each change that you trigger from the code. This frame, in order to produce a new frame, in order to produce 60 frames per second, which is the average, which is the value that you want in order to synchronize with the hardware refresh rate, you want 60 frames per second. It means that each frame has approximately 0.0166666666 and so on seconds, which is 16 milliseconds approximately. This is your budget for a single rendering, for a single time that the browser rendering pipeline has to run. But here's the catch, like the browsers are super fast and super optimized for this. In an ideal world, let's say, you can expect that the rendering pipeline takes about 6 milliseconds. I know, it's computed on an average website, average number of DOM nodes, average positioning, stuff like that. Let's assume it's 6 milliseconds. You might say, cool, problem solved, 60 frames per second, everything is smooth, I can go home, all done. What happens in the other 10 milliseconds? Well, we only talked about what the browser does. This is not our application code. Our application code needs to run in the other 10 milliseconds. And our application code means basically JavaScript logic, business logic, data fetching, DOM diffing, data processing, everything. Especially with our big fat JavaScript applications that we have nowadays in the browsers, it's a lot of work. So in the real world, most likely it will happen like this. First frame goes in 10 milliseconds, that's fine. It leaves room for the rendering pipeline to process and to produce a new frame. But then you have an operation like, I don't know, deserializing a JSON object or running some sort of long event handler that does some sort of data processing, and boom, you have 40 milliseconds. 40 milliseconds on a single threaded environment means that the next 2 frames cannot run the rendering pipeline. If during this operation there's a change on the screen, there's an animation happening, the user scrolls, the user focuses on an input, those will be dropped frames, which the user will perceive as a laggy application. It's also called jank, right? When you scroll and it starts, it feels like it's stuck for a few microseconds there. Let's do a quick audit to see how this actually looks in the browser. I'm going to go to, do we have any Formula 1 fans here? Okay, a few hands raised, cool. Okay, I'm going to audit their website, which honestly sucks big time. Like, just before I was trying to load it up on the slow 3G network in the room, and it took forever to load, so definitely not optimized. But that's a talk for another day. We assume that we have the website loaded. Let's see what happens when we start auditing here. So we have this performance tab in Chrome DevTools. I'm used with the Chrome DevTools, but all the browsers pretty much have tools for analyzing the runtime activities on a website. So you can click on the first button, on the record button, and after I click on the record button, I'm going to scroll through the website. New content will appear at the bottom. I can, for example, do like open the menu, go back, things like that, and then I'm going to stop it. And this will now load the profile of what just happened. It will show all the functions calls that got executed during this operation, during me interacting with the page, scrolling, clicking, dropping down the menu, and things like that. This looks terrifying at first. I totally agree with you. But it only gets better and better as you practice with the rendering tool. You will get something called the flame chart. This is the exact number, the exact stack trace of your website, all the functions that the website called during the operation. You get the frames per second wait, I can zoom in a bit. Is it okay? Visible in the back? I need a hand in the back. Cool. So you get things like the frame rate, which is the green line that goes up and down, as you can see here. You get the amount of time that the browser spent executing JavaScript versus the amount of time that it spent executing rendering operations like paint and composite. This is the yellow versus the purple color here. And very important, you get messages, hints of places where there might be something you can do, like, hey, a recurring handler took 147 milliseconds. Remember the 40 milliseconds example, right? 147 means 8 frames that were dropped. So if this occurs, regularly you can go down all the way to like 10, 15 frames per second rendering. You also get messages like, I hope I get one, yeah, here. Forced reflow is likely a performance bottleneck. So only by auditing the website, you already start seeing errors, like messages, hey, and you start Googling, like, what's the deal with this? This is basically how you get into performance. It's not like you take a course. It's not like you go to university, to the performance university of JavaScript. You can actually just use the DevTools, find out what the problems are on real websites, on your own applications, and figure out by reading the documentation, understanding what the problem is there, trying to figure out the problem and trying to fix them. It's the best way that you can learn it. Okay, enough about the auditing part now. Let's have a look after. Now let's check. After we have the audit, right? This is the first step. We need to be aware that, hey, this website might have some potential problems. Now let's talk about those specific things that I mentioned, like the small areas, areas of concern that you can follow, you can look into, and you can bring back in your day-by-day activity and just make sure that performance-wise you are not impacting the website in a negative way. So we're going to talk about 3 particular areas of interest here. First one is the DOM access. Now, DOM access is tricky because it's pretty time-consuming. From the perspective of, again, the single-threaded environment, DOM access is one of the most expensive operations that you can do on a running website. That's why a lot of modern frameworks don't even allow you to do direct DOM access, and they will do it for you with an optimized approach. But let's say, for the sake of it, that we are dealing with direct manipulation of the DOM. And you will see here that it's not only that, there are a lot of situations when even when you would have a virtual DOM, you still can easily cause headaches for in terms of like performance and the amount of time that the browser needs to spend on DOM manipulation. So first off, multiple DOM accesses. Of course, this is more problematic. One DOM access is what you usually have to do. The virtual DOM will have to do that DOM access at some point. It's not like they don't do it magically. But the problem is, like in a scenario like this, let's say that you are, like I did on the website. I was scrolling and I was getting new items, new news items, like loaded in the bottom of the page. You might have some system that gives you additionally like 20 items at some point. So the code would be like, you would do a for loop over all those 20 news items. You would create a box, a news box for each individual item. And you will, at the end of the for loop, you will append that box to the wrapper, to the container that keeps all the news items. This is, of course, problematic because this is a synchronous call. This is a single function executed at some point, which triggers 20-something DOM accesses during this time. So this can get very tricky very fast. Imagine if you're having this infinite scroll kind of ability and you're loading 20 news items every couple of 100 milliseconds because you're furiously scrolling down the page to catch maybe the footer, which is not accessible because infinite scrolling. Yeah, that's a talk for another day again. There's a link here about a case study on DOM performance. It's really interesting to read and to find out maybe some tips and tricks on how to make this kind of situation better in real time, in real life examples. One particular problem with the DOM access is what is called the involuntarily layout trigger. So consider this example where you have a header and you have an event handler on scroll. On the handle scroll function, inside it, you will have a condition, right? If the scroll position is greater than 50, let's say, the next line is change the position of the, change the style of the header to a fixed position. This is like a sticky header implementation if you want. So the third line, the one that changes the style, as mentioned before, any change in the DOM that is triggered by JavaScript will trigger the rendering pipeline. The problem is this one, the second line, the Windows scroll Y. Turns out the browsers, again, I'm praising the browsers here, but the browsers are really, really smart and heavily optimized. And the browser does not compute these values on every, at millisecond precision, because that would just drain resources, right? So when you're calling this kind of function, you are forcing the browser to perform a layout operation and figure out what's the value of the scroll position. And turns out there are a bunch of these functions on the DOM APIs which are triggering these layouts. I had no idea. I found out this, I was like, whoa, I'm just reading a value and I'm causing a performance issue, that's bad. But turns out like things like offset left, offset top, I'm pretty sure you used some of these in some scenario, even if you're using React or Vue or whatever the hottest framework nowadays is in JavaScript, you might have some scenarios where you might be using something like this. There's a gist here at the bottom written by Paul Irish quite a while ago on all of these. This is just a small section of all the functions, of all the properties and functions that are triggering this layout. The problem here is not only, okay, let's say the layout is fine. The browser can compute the layout also very fast. But there's a problem of resource allocation here. A forced synchronous layout most of the times will trigger what is called the layout thrashing. Same example again. This is when you see this example. Forced reflow is likely a performance bottleneck because you have the second line, the scroll Y position. The browser needs to compute the entire layout. And then what you do on the next line? You change the DOM, so the browser has to recompute the layout, right? So this is like pretty much a useless operation that happened one line before. Imagine if you have this running multiple times in event handlers, that it can actually lead to a lot of performance bottlenecks. And you will see this very often on when looking at through the dev tools. Like forced reflow is likely a performance bottleneck. This is most likely the cause of it. Okay, done with the DOM access, let's talk about JavaScript. I need a sip of water because talking about JavaScript is going to take a while. The first thing you want to look in terms of JavaScript and performance at runtime is event handlers, because that's the entry point to any change, to any user interaction. And again, coming back to the example, remember the long-running tasks, like 100 milliseconds a task. If that task is triggered by some sort of timeout, let's say, and there's a data fetching, but the user is not interacting with the page at that time, that's fine. That doesn't affect performance. But event handlers, 90-something% of the cases, event handlers are user-triggered. So the user wants to focus on an input, the user types something in an input, the user scrolls, the user hovers over something. All of these event handlers, if the handler itself takes too long to run, it will cause the user to wait, to have those drop frames and to feel that, hey, I just click here, why does it feel like it's janky? Why did the scroll jump? You know, this is when you get that kind of janky activity. And again, the dev tools are really good at this because they figure out all the event handlers which are taking, I think there's a threshold of 100 milliseconds that, and it's triggered there. It has a small red corner that says, hey, this event handler is taking too long. So a good idea when you have this kind of problem is maybe to defer whatever action. For example, most of the times on an event handler you might be data processing something, then calling some sort of backend API. You can try to maybe dispatch that on a separate event, depending on the architecture. Like, for example, if you have like a Redux style architecture, you can try doing a set timeout to simply allow the handler to run and the visual change to happen on the screen, only then your actual code to run. So there are a lot of things that you can do here to change the way in which handlers are affecting kind of like performance. The next thing about handlers is not only how much it takes for one instance of the handler to run, but how much it takes for, how many times the handler runs. When you do a scroll and you just listen on a scroll event, you might get it called, I don't know, 40, 50 times, even just by scrolling, tapping like for a few 100 milliseconds on the screen. So in this case, you want to use event throttling. For those who are not familiar with the term, throttling is basically just saying, okay, event handler will only get called once every 100 milliseconds. With throttling, you can make sure that an event handler only is triggered, I don't know, at most, let's say, 10 times a second, which might be significantly less impactful on the performance than calling it 73 times during the same period of time. And there's an article at the bottom also with the difference between throttling and debouncing. If you want to use debouncing on inputs and stuff like that, you can read the article and find out more about it. One quick thing that you can fix, which is, I don't think is that well known, is the passive event listeners. So touch and scroll operations are, again, optimized by the browsers. So the browser can do the scrolling on a separate thread. But if you're attaching an event handler to the scroll, the browser has to wait for your event handler to finish, because you might call prevent default and the browser should not scroll. So with passive event listener, you're instructing the browser to optimize the scroll, and you're making a promise that, hey, I won't call prevent default on this event. You just optimize the scroll. I'll just do my thing on the handler. It's basically like I said in the beginning, it's deferring the work of the handler until the visual change can happen first. So the visual change will have the priority. There's a video here. Hopefully it works. You can also read in the docs more about passive event listeners. You just have to put the passive true parameter when you're attaching the event listener. But internet connection. So it's instantly visible the difference between a passive event listener and the option without that. It's interesting that CNN is usually used by a lot of performance, like a lot of examples of performance, and you would imagine they would do a better job by now, but apparently still. Okay. Finally, animations. Yeah, right. The juice of all applications, the fun part, if you want. Animations can be optimized from two perspectives because there are two types of animations. JavaScript animations have a very, this is not a very common case, I agree. But if by some chance you need to animate something from JavaScript, and you have your own custom animation in JavaScript, it's very important to use request animation frame, because in a function like this, where you have an animate box function, right, which sets the margin. This is a very stupid example, I know, but just bear with me. So you are setting the margin, for example, for a box. You're computing the margin in the function, and the last call of the function is a request animation frame of the same function. So the other option would be to do like a set interval, right, or a set timeout. The problem is that that just runs in the regular event queue, like in the event loop of JavaScript. With request animation frame, you are syncing the function with the rendering pipeline. So you are assured that the animate box function in this case will run exactly before the rendering pipeline at the end of the frame, which ensures you that this function runs, if you have a 60 frames per second animation, this function runs exactly 60 times. You won't get that with a set interval of 0 or of 60 milliseconds. Never. So this is very important. But now moving to the CSS animations, which is probably the most common use case of, the most common case of animation. Coming back to the rendering pipeline. Style, layout, paint, composite, right? Hopefully by now you remembered them. What if a CSS animation starts with a style and then skips the layout part and goes with paint and composite? Or even better, what if it starts with the style? It needs style, right? It needs to compute the style, that's inevitable. But what if we skip the layout and we skip the paint and we just run the composite layer, just the composite level? Luckily, some CSS animations have this ability. On csstriggers.com, you will find a complete list of which rules trigger which steps. But it seems like a bit complicated if you look at it's a table, also browser implementations can differ. There's one trick of remembering it. If it changes the geometry of the element, is it a width animation, max height, height, whatever animation you're using that triggers some sort of change in border, margin, stuff like that, sorry, but it will trigger layout, paint, and composite because it has to recompute the entire structure of the DOM. If it's only a visual property, if you're animating the color or the background color or the visibility of an element without taking it out of the DOM, in this case, you get away with a paint and a composite. And if your CSS rule is promoting an element to a new layer, which is what transform and opacity do, you will get only composite. So it's super important if you're noticing, for example, slow animations. You can try in DevTools. I didn't show this. In DevTools, you can run your CPU with a simulated like 4x or 6x slowdown. And if you notice that the animation starts looking like janky and all, it might be time to switch, for example, from a height-based animation of a drop-down to a transform translate-based animation. Or you can switch to opacity, something that used to be, I don't know, whatever else. Now, I don't have time, unfortunately, but I have this Sandbox that you can also check online. It's going to get slow anyway because of the network connection. And in this code Sandbox, you can check how two boxes are moving. I made boxes in the Sandbox. So two boxes will be moving on the screen, and you can play with animating them by margin, and then animating them by translate. And furthermore, there's one final touch to this. In case the browser cannot figure out that, hey, this element needs to be promoted, there's this trick here called will change. Not sure if you see the code exactly. I'm just want to say this and then I'm off. So will change transform will tell the browser, hey, promote this element. I can assure you that I will do some animation with it. For example, here I'm writing the animation in JavaScript, so the browser just looks at the CSS, doesn't know that, hey, this element needs to be promoted. So when you do will change in this example, you will be able to, where am I? Yes. You will be able to have smooth animations without triggering layout and paint. Keep in mind with will change that you should only use it as a last resort. You should not do will change on any element because composition, it comes with a cost at the end. And make sure you test everything and you just introduce it after you know that it's the only thing that left to do in optimizing it. So, quick recap. We talked about these things today. I don't want to read them all. You can follow along the slides. There are a bunch of resources. I think I have more, but I simply didn't fit more on the slide. A lot of links on this. Come find me afterwards if you want to talk about anything from CSS animations to stuff related to anything I talked about or anything I didn't talk about. Would be more than happy to interact during the next break. And thank you very much for having me, and have a lovely day.